Okay, so we are back at capacitors looking at, so today we're going to look at dielectrics in capacitors and energy in capacitors. Okay, and so this is where we left off last time, that capacitance is the charge over voltage. And remember what I said there, this is not telling you what is the maximum amount of charge a capacitor could hold. That's not what capacitance is. What capacitance tells you is how much charge it could hold at a specific voltage. With more voltage, you could, of course, hold more charge. Okay. Now, what we're going to talk about today with dielectric is that there is a limit there that capacitors could hold. So let me show you what I mean here up on the screen. Let's say I had a capacitor. Whoops. Where's my pen? Okay, and I just say this is positive charge here, this is negative, and I start to build up the electric field. So electric field starts to go here. Okay, this is my electric field. Okay, so what's going to start to happen if, let's say I were to increase the voltage. So I'm increasing the voltage in my capacitor. That voltage is building and building, charge is building and building. So according to the equation you see on the screen. Okay, so the more charge gets built up, right? Remember, the equation for electric field is eta over epsilon zero. So the more charge gets built up, the stronger the electric field becomes. Eventually, this electric field is going to be so strong that we're going to have something called dielectric breakdown. And what that means is that the charge here, this charge here is going to be, well, I guess the electron, but either one. This charge here is going to be able to cross over here. And once that charge is crossed over, we no longer have a capacitor, right? The plates aren't being aren't holding charge anymore. Okay, so that's called dielectric breakdown. I'm pretty sure I have it later in the slides, but I'll write it now. Okay, and so in dielectric breakdown, you start to have this charge on these capacitors. The capacitor cannot hold any more charge there. The electric field is strong enough to move the charge from one plate to the other, and as soon as that happens, you don't have separation of charges anymore, and then you don't have a capacitor. Okay, so that's dielectric breakdown. So we want to be able to store more charge on the same capacitor, but without having this strong electric field. So so here's kind of the answer to this. So we can store more charge and therefore more energy, which we'll get to in a second. More charge if the E field is weaker. I don't know why it does that. Okay. Okay, so we can store more charge if we make the electric field weaker, and that is where dielectrics come in. Okay, so the whole point of dielectric is to make the electric field weaker, and thereby giving us more where it could hold more charge in a capacitor. Okay, so that's where we're headed today. Let's see here. So let me go here. Okay, so what's going to happen once you put a dielectric? Actually, before I get this, I would like to draw before I get to the PowerPoints. Okay, so how do dielectrics work? Give myself as much space here. All right. So first of all, a dielectric. Can I define that? A dielectric is an insulator that is placed in between plates of a capacitor. Okay, so let me draw this out and show you how that looks like. So here's my plates. Again, I'm going to make one positive. The other one's negative. Okay, and I'm going to put this dielectric in here. Okay, so usually I have the electric field, right, going from here to here, right? That's my electric field from the plates. This dielectric, remember, charges in an insulator cannot freely move around. All right, so we're not going to see a polarization effect here. What we do, like a complete polarization, negatives won't go on the far left, positives won't go on the far right. Okay, so we're not going to see that dramatic polarization. What we do see inside a dielectric, I'll do this in blue, I guess, is that you get these local polarizations. All right, so I'm only going to draw two more here. Okay, you start to get these local polarizations there, and those polarization that polarization is going to decrease the electric field. Okay, because you can see that if the negatives and positives are pointing that way, you do get an electric field within this dipole here. You do start to get these polarizations there with the electric field going this way. Okay, so this is the electric field inside these dipoles. So those electric fields are going to diminish the electric field from the capacitors. Okay, so let me write that up here. So the local polarization, which occurs in the dielectric, weakens the electric field from the capacitor. Or in the capacitor, I should put from. Okay, and if it does that, that means more charge can be placed on the capacitor before you have dielectric breakdown. Okay. Now there is still a dielectric breakdown, right? Once you put the insulator there, that just changes, how much electric field before you get dielectric breakdown. Usually, the insulator gives you more, allows the electric field to get even stronger before you have that breakdown. So usually, it's a lot better than vacuum, a lot better than air. Okay, so you can still have dielectric breakdown. There's still that upper limit of where of what you could get before the electric field causes a charge to go from the positive plate to the negative plate, or vice versa. Okay, so but it like I said, it pushes that ceiling up so that you could actually put more charge there. Okay, so that's what the dielectric breakdown is, and so to measure this, we use something called a dielectric. Let me see. Let me move stuff out of the way here. All right, we use something called a dielectric constant. So dielectric constants. Okay, so a dielectric constant takes this electric field that you see in the picture, the red electric field, and compares it to the electric field you would have in vacuum. So I'm going to draw one more picture here of it. Oh, let me do it in black. Okay, and so this, I'll call this my E0. Okay, this is going to be the E field in vacuum. Move this over. Okay, so the dielectric constant looks at what is this ratio between the E field when you put a dielectric there and the E field in vacuum. So dielectric constant is going to be K. That's the symbol, and I think it's actually like a kappa, so it's a Greek letter. It's the electric field when you have dielectric divided by the electric field, no, other way. Electric field in vacuum divided by the electric field when you have a dielectric. Okay, that is the definition of this dielectric constant. Let's see here. Let me do this in. So how does this change charge, capacitance? Yeah, how does it change all the different things about a capacitor? Okay, well, let's talk about voltage first. I think voltage is a good place to start. We said voltage. We said voltage is E times D, and that's still going to be true. It is the electric field. Remember the E. If I put E, I'm talking about the electric field with a dielectric. E0 is the electric field in vacuum. Okay, so using that equation above there, I could substitute E0 over K times D, which E0 times D is your initial voltage over D. One thing I forgot to say about dielectric, let me put a note here. Man, wish I could put subscripts. Okay, so one thing, this is my note that I forgot to write earlier. Since the electric field in a vacuum is always going to be greater than the electric field when you put a dielectric. Remember, the whole point of the dielectric is to weaken the electric field. The dielectric constant will always be greater than 1. Okay, so applying that down here, I made a mistake. It's supposed to be K. Okay, so applying that to the voltage, K is always going to be greater than 1. So when you put a dielectric there, your voltage you would otherwise have in a battery, otherwise having your capacitor, is now going to be less. Okay, so if K is greater than 1, right, you plug in, you look at this ratio, your voltage divided by K is greater than 1, it's going to give you a smaller voltage there. Okay, so voltage is going to decrease unless you have it connected to a battery. We'll do that example next. What happens when you connect it to a battery? we'll see what happens to voltage. We could talk about charge. And before charge, let's talk about capacitance. So for capacitance, well, we know C equals, let me use this equation. All right. Let me do it this way. Okay, Q over V. That Q over V, the Q is the charge on the capacitor. So in both these pictures here, this, oh, wrong one. This picture here and this picture over here, they're going to have the same Qs, right? I didn't do anything. The only difference I did here was insert the dielectric. These two had the same charges, okay? So they're going to have the same Q. What's different is of V's, right? Like we talked about this V here. So if I plug in what my voltage is, my voltage here is going to be Q over V0 over K. And that's just KC0. Okay, Q over V0, charge over your voltage, is your initial capacitance, right? Capacitance in vacuum. So Q over V0 becomes C0, and then of course we still have that K, right? K is the denominator of a denominator, so that brings it back up into the numerator. Okay, so what this is telling me is that if you insert if you insert the dielectric into a capacitor, K being greater than 1, you're going to get a larger C, larger capacitance. Okay. So let's do one more. Let's do charge. Charge is pretty easy. Q, whoops, I already said it, but I'll write it out explicitly. Okay. Okay. Okay, so this is when you can have a capacitor not connected to anything else. Okay. You get voltage decreases, capacitance increases, and charge stays the same. All right, so I'm going to look at a separate case here when we have a battery. If I connect a battery and I do the same thing, I insert a dielectric into a capacitor. These things change a little bit. So we're going to go over what happens in that situation. Okay, so it says voltage increases and capacitance decreases. No, so okay, when we say increases and decreases, what we're comparing is the capacitor when it's empty, when it only has vacuum, versus the capacitor to the dielectric. All right, so I have an empty capacitor, and then I put a dielectric in that capacitor. Okay, in putting that dielectric in, voltage is going to decrease. This is my initial picture, right? I have a empty capacitor, and then I put the dielectric in. Okay, so here, this is my initial, here's my final. All right, and doing that, right, this is what we did over here. Voltage is going to decrease, and since voltage decreases here, the denominator goes down, capacitance goes up. What is an example application of a dielectric? Oh gosh, pretty much any capacitor that your phone, inside your phone, pretty much any electronics has capacitors. You can't really make capacitors with vacuum in them anyway. Just in constructing them, you're going to have to, these plates are going to have to be held somehow. And so you're going to put it in, like you could put paper in there. There are a lot of a lot of research that goes into what it would be a really good dielectric, so you get the maximum capacitance. So I don't know. Was example of that's it's kind of like one of those things that it's just everywhere. Anything that has any electronic, it's going to have some kind of capacitor, and so a lot of times we want to make that capacitor hold as much charge as possible. So I know I didn't give you an exact application, but they're kind of too numerous. Now I have one coming up in the slides, so you kind of see one application there. Okay, so let's go back to the slides here. All right, so I like drawing them out better than using my slides, but it's a good recap. Okay, so in my slides, where is it? Okay, so this is what I pretty much just described, right? You have an empty capacitor with a certain charge in it. You put the dielectric in that capacitor, and putting that dielectric in the capacitor, the electric field gets weaker. Okay, so with the electric field getting weaker means we could put more charge in the capacitor. All right, so this is summarizing what I just talked about there. And then same thing here. Well, actually, you guys are doing a virtual version of this homemade capacitors. So usually we do a lab in class to look at the behavior of capacitors, but you guys will do a simulation online. Okay, so here's our equation for capacitors. We talked about this equation last time. This equation changes a little bit. Instead of epsilon zero, for a capacitor, once you put it, so epsilon zero is what I wrote over here, is a permittivity of free space. We don't, essentially vacuum. We don't have vacuum anymore. Once you put a dielectric in your capacitor, you don't have vacuum. And so that you can't really use that epsilon zero. We had to change that a little bit. And it becomes epsilon, not epsilon zero. Okay, so it's just another way of taking into account the dielectric, where epsilon uses that dielectric constant. Okay, so just yet another way of taking into account the dielectric constant there. We actually saw this, or I mean, you could get this pretty easily. Remember, we saw. Let me add a quick note here to see how you could get that. Okay, we saw C. Oops, my pen. C equals K C0. Well, C0, you know, you have up there in the first equation on this page. So all I'm saying is that this epsilon zero here, this epsilon zero is just these two multiplied together, right? K epsilon zero. Okay, so like I said, it's just another way of taking into account the dielectric. Instead of epsilon zero, you have a new constant epsilon, and epsilon is related to epsilon zero, but it's just dielectric constant times epsilon zero. So some examples of dielectrics here. You can see they're constant, and then dielectric strength. That's when you get that breakdown. So you can see as you start to put in things in between your capacitors, your dielectric constant goes up, and as your dielectric constant goes up, then your dielectric strength goes up. Okay? Again, once your electric field exceeds these numbers, that's when you have that breakdown. And once you have that breakdown, that capacitor ceases to function. Okay, so we don't want that breakdown. Okay, but that's why we put these things are here. Look at strontium titanate, 300. And it says water here. I'm guessing this water somehow is insulated from the plates. Okay, and then you could actually go below. There are materials stronger than strontium titanate, and in that case, when we get stronger than that, you know, this dielectric constant shoots way up, and that's an active area of research, right? What are these other materials that could really give us a strong capacitance? All right, so just want to show you a couple of numbers here. Okay, so we did that one. Okay, let's talk about energy, and we'll come back to this problem. So let me go here. Let me see what time is it. Okay, let me talk about energy, and then we'll take a break after energy. No. All right. Okay, so energy and capacitor. When we start off with an empty capacitor, we start off with an empty capacitor, and we're going to connect it to a battery here. Okay, I think we talked about this last time. That's a symbol for a battery. You have a long line, that's the side of the battery that has a higher voltage, and you have a short line, that's the side of the battery that has a lower voltage. Okay, so in other words, this would be the positive end of the battery here, and the other side would be the negative end of the battery. Okay, so we have this battery, we have an empty capacitor. What that battery is going to do, it's going to start charging up this capacitor. So it's going to start moving a charge onto that capacitor. Okay, so we know how much potential energy is stored up in that. Let me see, what's the best way? I'm trying to think what would be the best way to approach this. I could do it during voltage, or I could do it using energy. Let me do it this way. So for one charge, so for some charge, I'm going to call this dq. Because eventually I'm going to put more and more charge, right? A Q, capital Q would be my total charge. So this is not my total charge yet. This is just moving one little piece of charge into the capacitor. And for that one little piece of charge, I get a small amount of energy. All right, Q, let me see, let me go back. dq times V, right? Okay, so where did I get that equation from? Well, we saw last time that U times Q times V is energy. This time I'm moving one piece of charge, or one little charge on there. So I get for a small change in charge, my dq. So for a small dq at a certain voltage, I get a du. Okay. Well, this voltage, if we're talking about capacitor, that voltage is related to charge. Remember, capacitance equals Q over V. Okay, so I would need to make a substitution here. Du equals dq times Q, and that's not total charge. Well, but this is Q over C. Okay, so to find the total amount of energy here, I am going to have to integrate. Okay, so I'm going to integrate both sides. And I'm going to integrate this side from having zero charge, which is what it starts out with, right? This capacitor starts off with zero charge. And I'm going to keep putting charge on there until I get some total charge Q. Okay, so the right side becomes U. The left side, I could take out the 1 over C. Let me just make sure I did that algebra right. Yeah. And I'm going to integrate Q dq. Q dq from 0 to Q. Okay, so doing the integral, I get 1/2 q squared over c. And there we go. So this is how much energy I have in a capacitor. It's not just, okay, so this equation up here, oops. This equation up here, this one, does not apply to a capacitor. The reason why it doesn't apply for capacitor is that Q is changing, and as Q changes, voltage is changing. So voltage is a function of Q. Okay, so this works for a point charge. Okay, it works for a point charge. It doesn't work for a capacitor. We had to do all this integral stuff, and then we get the equation for capacitor. And that's not the only equation. If I use the same equation I have up here, and oops, and make different substitutions. Oh, what am I doing? And make different substitutions into that equation, you know, I get different equations. So I could get making different substitutions. You get 1/2 CV squared, or 1/2. What would be the other one? 1/2 QV. What? Yeah, 1/2 QV, right? I hope I'm doing my algebra right. Okay. All right. So that's energy in the capacitor. Now, when you put up, if we put a dielectric there, that energy is going to change. So let me see here. Okay. So you put a dielectric there, energy is going to change. Why? Because C, your capacitance, you know, equals KC0. So anywhere you see a C, that's going to change it. It does change Q also, right? It changes Q and it changes V, but I'm going to talk about that because we have a different situation here. In this situation, you have a battery connected. So I want to wait until after the break to talk about what happens when you have a battery connected with the dielectric. What we saw earlier is not, a lot of this isn't going to hold true. So voltage actually does not change. Charge will change when you have it connected to a battery. In an example we did earlier, we don't have it connected to a battery. It's just a capacitor sitting, a charged capacitor sitting, you know, out somewhere, not connected to anything. But now when we have a connected battery, it's going to change things. But what's still going to be true is this relationship here, that your dielectric constant is going to increase your capacitance. Okay, so we'll see what happens to energy there.